Hey y'all, it's me, Miss B, and today we are talking about continuity and limits. So I want you to look at these three graphs and I want you to list the similarities and differences between them. The main point you should have made is that if you can draw all three of these graphs without lifting a pencil from your paper, you cannot draw any of these graphs without lifting a pencil from your paper. So we have a gap here, we have a gap here, and we have a gap here. So now we're going to jump into some definitions. So a function is continuous at A when these three conditions are satisfied. First, A has to be in the domain of F, which basically means you're going to plug A in. Second thing is that the limit as x approaches a of f of x needs to exist, so it needs to be a real number. The third thing is that the limit as x approaches a of f of x has to be equal to f of a. So we can actually use part 1 and 2 to do this part. Okay? If f of x is not continuous, then we're going to say that f is discontinuous. Okay, so here's our first example, and we need to determine whether this function here is continuous at a is equal to 2. So first we need to see if f is defined at a. So we need to find f of 2. So we're going to go ahead and plug 2 into our equation. So we have 2 times 2 plus 1 over 2 times 2 squared minus 2 minus 1. So that is 5 over 8, 7, 6, 5. Which is equal to 1. 1 is a real number, so yes, that is true. Okay, so I'm just going to make a little note that f of 2 is equal to 1 because we're actually going to use that later. All right, condition 2. The limit of f of x has to exist, so I have to see if this limit exists. So I'm going to take the limit as x approaches 2, and let's go ahead and factor this. So I have 2x plus 1 over, let's just do the guess and check. So I need two numbers in for this, and they have to multiply to get -1 and 2 negative 1. So I need this to be -1 and this to be +1. So then, oopsie daisies, these are able to cancel, and so we have the limit as x approaches 2 of 1 over x minus 1. I'm going to move this up here. Make this a little bigger. Move it down. Okay, so these two things are equal. Then I plug the 2 in, and I get 1 over 1, which is 1. So the limit as x approaches 2 of f of x is 1. Okay, and I'm going to put a little box around that because that's important. Okay, my third thing is that my limit of f of x and f of a need to be equal to each other. So I'm going to use this information here. So this purple one is right here, and then f of 2 is in the orange. So I just set those two things equal to each other. So I have 1 is equal to 1 because those two things are equal, because all three conditions are satisfied. the limit or the function where's my pen? Is continuous. All right, so that's one example. All right, and here's an example of a piecewise function here. So we've got a piecewise function, and we are trying to determine where it is discontinuous using some algebra. So we should check to see if it's discontinuous at these points here. So we're going to check at x is equal to 0 and x is equal to 1, because those are the points where it's transitioning from one function to the other. So go ahead and roll through the same thing, starting with x is equal to, let's start with 0. Okay, so what I'm going to do is I'm going to check all three of these to see if they're defined at a. So I'm going to plug 0 in. So f of 0 is equal to, and I'm going to use this function right here because it's equal to 0, is equal to 0 plus 2, which is 2. Okay, so because it's defined, we're good, but I'm going to write a note, f of 0 is equal to 2, just to save it. All right, b, I have to show that the limit exists. So I am going to have to do the limit as x approaches 0 from the left and the limit as x approaches 0 from the right, because we have a piecewise function. So because we have a piecewise function, I have to test both the left and the right. So I need to find the limit as x approaches 0 of x plus 2 and 2. So that's from the left, and that's from the right. So I'm just going to make a thing here just so we can keep it in check. So then if I plug a 0 in, I have 0 plus 2, which is equal to 2. And this is also equal to 2. So I'm actually going to make this a little smaller. So because these are equal to each other, we have the limit as x approaches 0 of f of x is equal to 2. So that's also important. Now we have to see if these two things are equal, f of 0 and the limit as x approaches 0 of f of x. Since those are both equal to 2, the limit exists. So the limit is, let me write in regular handwriting here. So the limit is continuous at 0. All right, then we have to test at 1. So I'm changing color. Okay, so I have to do the same thing. So we have to find f at 1. So we're going to use this middle one here. That's just going to be equal to 2. Save that for later. Then I need to find the limit as x approaches 1 from the left and limit as x approaches 1 from the right. So I can find the limit as x approaches 1 two-sided. So from the left, it's going to be 2. From the right, it's going to be x squared plus 2. So we'll plug that value in, that's equal to 2, and this one's equal to 1 squared plus 2, which is equal to 2. Because those are equal, the limit as x approaches 1 of f of x is 2. Then f at 1 and the limit as x approaches 1 of f of x, those two things are equal to 2, so the limit is continuous at 1. So the limit is the function, I should have said function here. All right, we'll just so the function is continuous everywhere. Okay, so let me check my work. I found it. 1 squared, dang it. I messed up, let's back it up. So 1 squared plus 2 squared is equal to 3, or I'm sorry, 1 squared plus 2 is equal to 3. So then the limit, that's a mistake there. So then the limit as x approaches 1 of f of x and f at 1, so we have 3 and 2, so those two things are not equal. So the limit, or the function, is discontinuous at x equals 1. So go ahead and make that correction there. All right, and that's all for today.